Hello everyone, welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over gas laws, and I'm going to be going over some preliminaries and the basics regarding gas laws, and then in other videos I'm going to go into more detail into each gas law and talk about that. But here in this video I'm going to be talking more of the basics and the preliminaries of gas laws. And if you want to know more about other gas law or the gas laws in more details, I encourage you to go see my other videos where I talk about each individual gas law and I go over the math and talk a little bit about the theory behind it, the kinetic molecular theory behind the gas laws. Okay, so let's get into this. Okay, so some preliminaries regarding gas laws. So the first thing I want to point out is we should always be using the Kelvin temperature scale for temperatures. And the way you get Kelvin from your degrees Celsius, which in a lot of cases you're going to be given degrees Celsius, and you want to convert that to Kelvin when you're using your gas laws. And so here, this is the equation you want to use. So in order to get to Kelvin scale, you take your Celsius scale and you just simply add 273.15 to that number. And then voila, you have the Kelvin scale. So why do we want to use the Kelvin scale? Well, because if we use other scales like Fahrenheit or Celsius, you can get negative numbers because you can have negative temperatures. So if we're relating, say, temperature to number of moles or temperature to the volume of a gas or the temperature to the pressure of a gas, if you use negative numbers for the temperature, then you're going to end up with negative numbers for volume, for pressure, and things like that. And for example, it makes no sense to have a negative volume. You can't have a negative volume. How do you measure a negative volume, right? So to avoid those sorts of absurdities, we use the Kelvin scale because the Kelvin scale is absolute zero, which means that you can get to 0 Kelvin and you can't have a negative number. You can't get negatives because the idea is that when you use the Kelvin scale is set up in such a way that you can get to zero and you can't get any lower to zero. That's why we call it absolute zero. You can't get a negative temperature on the Kelvin scale, and the reason for that is because it's based on this idea that there's no molecular movement at that lowest temperature, right? So when we're linking up the movement of particles to temperature, we've learned before that according to kinetic molecular theory, temperature is linked to the speed of molecules. So faster molecules are at a higher temperature. So if you raise the temperature, you are increasing the speed or the kinetic energy of the molecules. And so that means that there should be a temperature at which the molecules stop moving. And so that would be the absolute lowest temperature you could get. And so zero on this scale is the absolute zero. So you can't go below that, right? So that's the reason why we use the Kelvin scale. Now, just to throw a little nugget out there, you can actually get negative Kelvin temperatures, but that's for another video. So we'll leave it at that. So sorry, that's a teaser. Okay, second thing is units of pressure. So we need to use units of pressure to for some of our gas laws, and so you need to know how to convert between certain units of pressure. Um, so you have these units of pressure that you need to know how to convert between. So 1 atmosphere is equal to 101,325 pascals. So that's equal. So you should be able to convert between those. 101,325 Pascal is the same as 101.325 kilopascals, which is then equal to 760 millimeters of mercury, and which is equal to 760 torr, which is then equal to 14.7 psi. Psi stands for pounds per square inch. So these are the units and the equalities relationships between each of these different units of pressure. And so you want to be able to convert between them because they're fairly commonly used. Probably the most commonly used is going to be atmosphere and millimeters of mercury, and also torr is commonly used, but the others are also used as well. So you're going to want to know how to convert between them. So you want to memorize these relationships. And third for our preliminaries is STP. STP stands for standard temperature and pressure. So standard temperature is 0 degrees Celsius or 273.15 Kelvin. Standard pressure is going to be 1 atmosphere, and that's again equal to 760 millimeters of mercury. So whenever you see 760 millimeters of mercury or 1 atmosphere, that's going to be standard temperature and pressure. So 0 degrees Celsius and 1 atmosphere are the standard temperature and pressure. And so you want to be able to recognize those in these units as well. And so that's going to be useful as well, because under standard temperature and pressure, we can know how much of a gas or we have per volume. So for example, where's my marker? So molar volume, right? So under these standard conditions, we would then know that 1 mole of any gas, doesn't matter what the gas is, 1 mole of any gas is going to be equal to 22.4 liters. So that would be a very important relationship that you could be able to use to do conversions. And again, this only applies under standard conditions. If you're not under standard conditions, you can't use this relationship. Okay, so that's it for the preliminaries. Let's get into the basic ideal gas laws. So the simple ideal gas laws, the simple gas laws, and we'll get to that in just a moment. Okay, so now I'm going to be going over some basic gas law equations. These are equations you should memorize. You should know what Boyles Law is. You should know what Charles' Law is. In case, if you are having conversations, right, or you want to talk about a certain law and you say, okay, I want Boyles Law this or Charles' Law that, you have to understand, or you have to understand what other people are talking about when they use these terms. So you should memorize what these laws are. In another video, I will talk about how really there's only one equation you need to memorize, and I call that the Uber combined gas law. I'll talk about that in another video. So let's get into this. So the first law is Boyles Law. So Boyles Law is a relationship between pressure and volume. It describes a relationship between these properties of gases, in particular pressure and volume. How does the pressure of a gas and volume of gas relate to each other? And so the way they relate to each other is inversely, or direct or indirectly or inversely. They have an inverse or direct relationship, which means they go in the opposite directions. So if pressure goes up, then volume goes down, or vice versa. If pressure goes down, then volume goes up. So that's an inverse or indirect relationship, and that is shown in this graph here. So you can see volume versus pressure. So as the pressure is increasing, you'll see the volume decreasing, right? So this is the graph showing that inverse relationship. So the P1 V1 equals P2 V2. In the way you use this equation is, again, the 1 and the 2 refer to initial conditions versus final conditions. So here, if you're given the initial pressure of a gas and you're given the initial volume of a gas, that should equal the multiplying of those two together should equal the multiplying together of the final pressure of the gas and the final volume of the gas. So for example, if I give you the initial pressure and the initial volume of a gas, and then I say, oh, here's the final pressure, and then I ask you, okay, what's the final volume? You can plug those in and solve for the missing piece. So this is the equation you would use for Boyle's law to solve a problem. And under these conditions, in order to use this, there's one important thing I need to point out is that temperature and the number of moles are held constant. So little n here, the little n or lowercase n stands for number of moles. T, of course, is temperature. So in order for Boyle's law to work or to be valid, temperature and the number of moles have to be held constant. Otherwise, you can't use this equation. So this equation, or Boyle's law, only applies under these conditions where temperature and number of moles are held constant. Okay, that's Boyle's law. Charles' law is this relationship here relating volume and temperature. So here you can see that the volume and the temperature, and again, remember, temperature is in Kelvin. We don't use Celsius or Fahrenheit for gas laws. So when you're looking at the relationship between volume and temperature, it's a direct relationship. So direct relationship, that means that if temperature goes up, then volume goes up. Means that they go in the same direction. If one goes up, the other one goes up. If one goes down, the other one goes down. And so this is showing you with the straight line that as temperature increases, the volume is increasing as well. So it's a straight line here. And so that's represented mathematically in this equation here. So V1 over T1 is equal to V2 over T2. And again, the way you understand this is that the ones are the initial conditions, the twos are the final conditions. So I could be given some initial conditions of the volume and temperature of a gas, and then maybe I'm given the final temperature, and then therefore they want to know what the final volume is. So I would plug in my values and solve for the missing piece. Right? Or I could be given the final volume and the final temperature of a gas, and then I could be given the initial volume of the gas, and they could ask me, okay, what was the initial temperature? So I plug in the values and I solve for T1, right? So that's how the equations work. Now, again, there are certain conditions under which this will work. So in order for Charles' law to be valid, pressure and the number of moles, again, N is the number of moles, pressure and the number of moles have to be constant. So if those are not constant, then this is not valid. So this is only valid under the conditions of constant pressure and constant number of moles. The amount of gas does not change. Okay? So the last thing I want to point out with regard to the graph is you'll notice that the graph doesn't go to zero. The reason for that is because we're talking about real gas particles here. So real gases, actual gas particles have volume, and so when you lower the temperature enough, right, you're going to get to a point where the volume is going to decrease so much that the space between the particles is at the minimum amount, but the particles themselves take up space. So there's always going to be a volume taken up by the gas. So you can't get to zero volume. You could go all the way to Kelvin, absolute zero, right? But that wouldn't take you to a zero volume because you're always going to have volume taken up by the particles themselves. Now, in a theoretical way, like hypothetically, in an ideal gas, one of the assumptions we make is that the gases are so small, the particles are so small that, or they don't take up space. And so you would theoretically get to zero, but realistically you never get to zero because you can't have zero volume with your particles. Gas particles are made out of mass, they're made out of matter, they have volume, so there's no such thing as getting to zero volume. So that's why it doesn't go all the way there. So some of these gas laws, the gas laws don't really apply at, or at least what we call ideal gas laws, don't apply at low temperatures and pressure, or high pressures, low temperatures. Okay, so that's Charles' law. So the next one is Gay-Lussac's law, and the Gay-Lussac's law is a relationship between the pressure of the gas and the temperature. And again, temperatures are in Kelvin, so that's why I have the K here. And again, you can see that the relationship between the pressure of a gas and the temperature is a direct relationship here. So again, direct relationship, straight line. This curved line here is indicative of an indirect or inverse relationship, and this is indicative of a direct relationship. And so again, the direct relationship is that if the temperature goes up, then the pressure is going to go up. And so this is the equation for Gay-Lussac's law. So it looks very similar to Charles' law. The only difference is instead of volume and temperature, you're looking at pressure and temperature. So again, the initial pressure over the initial temperature is going to be equal to the final pressure over the final temperature. And again, whatever you're given in a problem, you just plug in the values and solve for the missing piece. And again, for both of Charles' law and Gay-Lussac's law, you need to make sure that the temperature is in Kelvin. If they don't give you Kelvin temperature, you need to convert to Kelvin temperature. Otherwise, you're not going to get the right answer. And finally, I want to talk about, again, with regard to this graph, you'll see there's a dotted line there. And then theoretically, if you extrapolate back towards the graph here, it goes to zero. So theoretically, it goes to zero, but it won't go to zero. You won't realistically get to zero. And that's because the substances that we're working with, the gases, at low temperature, you're not going to have a gas anymore. You're going to end up having a liquid or a solid form because of the intermolecular forces that exist between the particles. Now, ideally, what the assumption is usually when we're talking about ideal gas laws or ideal gases is that there are no intermolecular forces between the particles. So they're not going to attract each other. They're not going to stick together. They're always going to be gaseous. But that in reality is not the case. So for example, you have liquid nitrogen, you have liquid oxygen. So these things exist because of intermolecular forces. So liquid nitrogen, in order to get nitrogen molecules to become liquid, you need to lower the temperature quite a bit until they move so slowly that the attractive forces can cause them to stick together, and then you're going from a gas to a liquid. And so those forces, remember those forces between the nonpolar nitrogen molecules are the London dispersion forces, right? So London dispersion forces exist, and so if you can slow those molecules down by lowering the temperature, then they can stick together and form a liquid. And so because of that, you can't go to zero with this graph because again, temperature and pressure. If you lower the temperature enough, you're not going to have a gas. So really, you're not going to have any pressure to the gas. So it doesn't work that way. So, but we can. It still applies under normal conditions, so it works. Okay, so I have two more gas laws to go over, and then that'll be it. So bear with me in just one moment. Okay, so this is the last law. I know before I said two, but I'm going to save the last one for another video. So, last law, Avogadro's law. So we've heard Avogadro before because we know Avogadro's number, the mole. 1 mole is equal to 6.022 times 10 to the 23rd. So we have a law by Avogadro. So this law is the relationship relates volume of a gas to the number of moles of a gas. And remember, the number of moles is represented by small n. And here you can see once again that it is a straight line. So this is a direct relationship. So as the volume goes up, so the moles goes up. So, and that makes sense. And you'll notice that in this graph, it does go to zero because it makes sense that moles can go to zero. So you decrease the amount of the gas, you can actually decrease it to zero. And it makes sense that if you have zero particles, you have zero volume, right? So in that case, it will go to zero. The graph does go to zero. And so here is the relationship, the mathematical equation for Avogadro's law. So again, V1, the volume, the initial volume over the initial amount of gas in moles, right? So V1 over N1 is equal to V2 over N2. So the initial volume over the initial number of moles is equal to the final volume over the final number of moles, right? And so here, N is the number of moles. It has to be in moles. It can't be grams, right? So it's got to be moles. And so once again, this relationship or this equation or this law only applies under the conditions of constant pressure and temperature. If you don't have constant pressure and temperature, then this law will not apply. This will not work, okay? So that's it for this video. In my other video, I'm going to be talking about the combined gas law. So that's where I bring all of this together and I show you that the combined gas law equation is really the only equation you need to know, because all of these other equations come from that one. And it all depends on what's constant. What properties of gases are held constant will give you the equation and the law that you want. But you still need to memorize which equation goes with which law. So if I say Boyles Law, you should know, oh, that's P1V1 equals P2V2. If I say Charles' Law, you should be able to come up with that equation. So you need to know and memorize those. That's important. So thanks for joining me. If you enjoyed this video, if you learned from this video, then please, by all means, like the video, right? Hit that like button right there. Share my video with friends. Also, make sure you subscribe to my channel. Hit that notification bell. And then when you hit the notification bell, make sure you click all. So that way you can be notified by any and all videos that I put out. And also, finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me. Have a great day.